In November 1983, the European Space Agency launched the first Spacelab mission on board the American Space Shuttle. The laboratory consisted of two basic elements: a reusable pressurized laboratory for scientists to work in, and a system of attached pallets exposed to the space vacuum. It was on the basis of the pallet system that ESA's member states conceived the European Retrievable Carrier, Eureca. This was to be an autonomous platform capable of carrying experimental payloads and remaining in orbit for months on end. Eureca has a total mass of 4,500 kilograms, 1,000 of which are devoted to experimental payloads. Its two solar arrays generate a total of 5,000 watts, 1,000 of which are allocated to the payload. This payload covers microgravity research, space sciences and technology experiments. Temperature control is maintained by a liquid freon loop, and the experimental payload is protected by multi-layer insulation. The guiding design principle behind Eureca has been simplicity and low cost. It's been designed and built by a consortium of European industries led by the German aerospace company MBB Aerno.
We have room for main engine start.
Eureca has been designed for launch by the American Space Shuttle. It's carried to an altitude of about 400 kilometers. The shuttle's remote manipulator arm lifts the space platform out of the payload bay. It's checked out, and then control is handed over to ESA's European Space Operations Center, ESOC, in Darmstadt, Germany. Eureca then climbs to an altitude of 700 kilometers, and here it will remain for 10 months. At the end of this period, Eureca descends to a 400 kilometer altitude, and the shuttle returns to rendezvous with the space platform. It's brought back to Earth for refurbishment, ready for the second mission. The scientific potential of Eureca is considerable. Access to the space vacuum and the environment of microgravity for long periods of time has been almost impossible for European scientists. Parabolic flights offer a few seconds of microgravity. Sounding rockets provide a few minutes. And even on Spacelab, only up to about 7 days. Some European experiments have been flown on the Russian space station Mir, but the success of this work has been mixed. In this respect, Eureca is unique. The bulk of the experimental payload on board Eureca is concentrated into material sciences. The reason for this is the exceptionally low gravitational disturbance associated with Eureca. This is very important to experiments, for example, in crystallography. On Earth, gravity has a strong influence on three basic physical processes that are fundamental to many manufacturing techniques. Convection of fluids, that is, how they mix. Sedimentation, how they separate. And hydrostatic pressure, meaning that the behavior of molecules at the bottom of a container is different to that at the top because of the downward pressure exerted by the volume of fluid above under the influence of gravity. These crystals, zeolites, are vital to industry because of their catalytic properties. Among other things, they're used to break down various molecular compounds in petrochemical industries, such as the manufacture of plastics. But synthetic zeolites produced on Earth for such industrial use are comparatively inefficient because of imperfections in the structure of the crystal, mainly due to gravity-driven sedimentation. In microgravity, there are no such restrictions. It should be possible to grow large, pure zeolite crystals, and this is to be tried on Eureca. The knowledge acquired may allow for the manufacturing of more efficient synthetic zeolites here on Earth. With expectations of such discoveries, scientists throughout Europe have welcomed the chance to fly their experiments on Eureca.
There are primarily two very important factors for crystal growth that we have on Earth, but not under microgravity conditions. One is sedimentation, and the other is thermal convection. Sedimentation means that after the crystals are formed out of the solution, they sink to the bottom, and there is no more growth. Whereas in space, under microgravity conditions, these crystals could continue to move around in the solution and could develop even further into larger crystals. The second phenomenon is thermal convection, which again is very important for crystal growth. We have this on Earth, but not in space, so we can expect better crystal growth under the microgravity conditions in space.
Ein besseres Kristallwachstum unter Bedingungen der Mikrogravitation im Weltraum erwarten.
Not all of Eureca's experimental payload is devoted to microgravity sciences. The space environment is equally important to other areas of scientific research. Space is a vacuum characterized by extremes of temperature and, around the Earth, subjected to various forms of solar and cosmic radiation. Among the odder theories being tested on Eureca is the idea that organic life did not originate on Earth but deep within the galaxy. This idea needs some evidence that primitive organisms, such as these spores, can survive in the harsh environment of space. Eureca is a perfect tool for this type of research, and just such an experiment is included on the first flight.
The Eureka mission is eine Langzeitmission.
The Eureka mission is a long-term mission. It will run for 6 to 9 months. This gives us the possibility to investigate how far microorganisms or organic molecules change and react on a long-term mission in space. In order to do this, we've exposed various biological systems, such as bacterial spores, fungal spores, biomolecules such as DNA or liposomes, under an optical filter system. They are exposed to full sunlight or selected wavelengths, and also to the space vacuum. In addition, control samples are exposed to atmospheric pressure. At the same time, we shall be exposing samples to darkness.
Befinden. Außerdem haben wir Dunkelproben, sodass wir einen ganzes Satz von verschiedenen Weltraumparametern.
Thus we can investigate a whole range of space parameters and their long-term effect on biological systems.
Eine der interessanten und wichtigen Fragen ist dabei auch, inwieweit
one of the interesting and important questions is how far the full solar spectrum, as opposed to the terrestrial solar spectrum, differs in its effects on biology.
Abweicht, inwieweit das unterschiedliche Wirkungen auf die Biologie hat.
But this experiment has a practical side as well. Depleted ozone implies higher levels of ultraviolet radiation on Earth. The long-term consequences of this are unknown, and the experiment should produce much new data. Eureca's simplicity and versatility combine to make the platform an impressively flexible research tool for microgravity research, deep space astronomy, and to test new technologies that will provide scientists with more support for their experiments on future Eureca missions. Eureca 2 and Eureca 3 are now in an advanced stage of planning, greatly extending the research opportunities available to a broad spectrum of European scientists.
All microgravity research undertaken up till now has been done on manned flight serviced by astronauts. Now, for the first time, we're keeping experiments in space for a long time and having to automate them. I see Eureka as a very important step leading on from what we can do today to the new future possibilities of a space station.